Good day, everyone. My name is Ixchel Hernandez. Thank you for listening to my presentation. Today, I'm going to talk to you about modeling and understanding the impacts of within-field heterogeneities on diversified cropping systems. About 50% of the global land use is allocated for agriculture. The challenges related to the trade-offs of farming and environmental impact have led to goals to shift towards more sustainable agricultural practices. Spatial and temporal crop diversification have been proposed as one measure for sustainable intensification. The practice has gained popularity in recent years as it can offer multiple benefits in terms of productivity, delivery of ecosystem services, and biodiversity. Moreover, within-field soil heterogeneities for physical and chemical properties may affect the spatial and temporal patterns of crop performance due to differences in soil nutrient and water availability. And here in these pictures, we can see two examples. So one is for lupine, where you can see that in the back, the crop has a much more dense canopy than the area in the front. So you can expect very strong differences in crop performance. Also here in the bottom, you can see the patterns of crop growth as NDVI for right around flowering. And you can see also some very distinctive patterns within this 70-hectare field. Understanding and managing these heterogeneities can benefit cropping system redesign by considering the trade-offs and synergies over times and scales. For this, we can use agroecosystem models, which can be an important tool to contribute to the understanding of the genotype, management, and environmental interactions. This approach may allow for better utilization of resource allocation by implementing management practices targeted to crop soil-specific characteristics, which may allow for increased crop diversification in our fields. But how can agroecosystem models contribute to the understanding and design of diversified cropping systems under heterogeneous field conditions? In terms of system understanding, we conducted a study to quantify the impacts of within-field heterogeneities on crop yield variability, as well as the interactions with climate. For this, we use very detailed soil data by layer from 49 soil augers collected at the patch crop experiment, which is an area characterized by very strong within-field heterogeneities due to past soil formations. We combine this data with daily climate data for a 30-year period from a station nearby. We use a process-based agroecosystem model within the simplest modeling framework to perform daily simulations for each of the soil augers over the 30-year period. Our results show that for this particular field, the spatial variability was higher than the temporal variability for most crops. Lupine and maize show the highest spatial variability, while sunflower and maize show the highest temporal variability among all of these crops. We also found that soil and climate effects varied by crop, and for this, we classified the soils and the seasonal rainfall into different categories. So for the soils, we used the plant available water capacity to classify the soils, where the category 1 had the lowest available water capacity, and the number 5 had the highest available water capacity. And for the seasonal rainfall, we did it similarly, where the seasons with the lowest seasonal rainfall were number 1, and the seasons with the highest seasonal rainfall for a specific crop were number 3 or 4. And here are the examples for 3 of the crops that we consider for the simulations. So we can see that for wheat and the soybean, the grain yield progressively increased as the soil water category increased. And then for the seasonal rainfall instead, the wheat yield is significantly increased as the seasonal rainfall increased. But for the soybean, actually, the highest seasonal rainfalls, they led to non-significant differences in the simulated grain yield. Then we found a significant interaction of soil and climate for the maize. We can see that for the soil water category 1 and 5, there's a significant increase of the grain yield from the seasonal rainfall category 1 to 2. And then when the seasonal rainfall was the highest, then the grain yield tends to be the same for these 2 seasonal rainfall categories across all of the soil types. Another thing that we can see is that the grain yield tends to be quite similar in the intermediate categories when the seasonal rainfall is the highest. I wanted to show you also an additional example where we apply the model to quantify the effect of the diversified crop rotations on soil moisture dynamics. For this study, we also use data from the patch crop experiment. But in this case, we created different rotations, which were simulated for 10 years. We used just 12 augers, which had very distinctive soil characteristics. And then you can see here the different rotations. So the baseline rotation is quite simple, just rye and maize. Then we have it together with Phacelia. And then we have two rotations that include cereals and legumes that are currently implemented at the patch crop experiment with and without Phacelia. And so here we can see the summary of this simulation for one soil auger. And this is the deep seepage. So how much water leaves the soil profile. And we can see that there was an impact of the diversified crop rotation in the soil moisture dynamics, where the diversified crop rotation B had a higher water seepage compared to the other rotations. Also, we can see that with the addition of Phacelia, which is here this bright pink or purple, we can see that with the addition of Phacelia typically led to a reduction also in the soil, in the deep seepage. So this is an example basically on how also diversified cropping systems can possibly affect also groundwater recharge. And our final idea is to combine actually our models with other data, such as soil proximal sense data for defining different management zones, to conduct virtual experiments for crop allocation and resource management, and to be able to design more sustainable cropping systems that maintain or improve crop productivity, but also that we can improve the resource use efficiency and promote the biodiversity in our agricultural fields. This study provides valuable information on how spatial and temporal dynamics are affected by soil and climate interactions, and it also shows the usefulness of agroecosystem models for system understanding. And with this, I would like to thank you for your attention.